Danger on the slopes, a projectile motion problem. Winter break had finally begun at Fred's school, and he had plans to go skiing with some of his best friends. After school, on the day that break began, he quickly packed his luggage and picked up his friends and drove off to the ski resort with them. Finally, after a long 6-hour drive to the resort, Fred and his friends made it and got all of their gear for skiing. Then they headed to the slopes once everyone was ready. When they arrived at the slopes, Fred almost immediately spotted a jump that went over a small valley filled with tall trees, and he wanted to attempt it to impress his friends. However, it turns out that Fred was a very inexperienced skier, so there would have been little to no chance of him surviving this jump if it wasn't for the fact that he was an AP Physics student. So, with the knowledge that he had, Fred decided to make some calculations in his head about what he needed to do in order to survive and impress his friends. He knew that in any physics problem he did at school, he had to make a free body diagram of the forces acting on an object before doing anything else. So he created a free body diagram for the instant before he would leave the slope and become a projectile. This is the free body diagram that Fred created. Since we know that Fn, or the normal force, would be pointing out directly perpendicular to the ground for any object, or ski slope in this case, we can draw it as a vector directly on the positive y-axis, since that's the direction in which the ground is pushing up on Fred. To find out where the force of gravity is, all we have to do is determine which way is down on the free body diagram. Then, since our free body diagram has been rotated around a little bit to line up with the position the object is in, we can have force of gravity pointing straight down from the origin. And these are the sum of forces equations that Fred also created. So, before Fred could go any further, he had to figure out the velocity vectors, as these would help him in his future calculations. Fred knew that he was going to be attempting to jump from a slope with a 30-degree incline, and with a constant diagonal velocity up the slope of 9 meters per second. Other values that he found would come in helpful for later in this problem was the height of the slope, which was 5 meters, and the length of the ditch that he had to jump over, which was 12 meters. This gave him ample information to be able to calculate his velocity vectors. So he derived two very short equations to find these velocity vectors, one in the x direction and one in the y direction, and then with a little bit of math he plugged in the values that he knew into those derivations, and that got him the magnitudes of the velocity in the x direction and the velocity in his y direction. After doing that, the first step that Fred needed to do was to solve for the time that he is airborne, since this would help him in finding how far he could go in the x direction later. To do this, he started off with the basic kinematic equation of y equals y naught plus vyt plus 1/2 at squared. Then he was able to rearrange this equation a little bit by simply moving the y naught to the left side and calling that whole expression on the left side delta y. Since we know the value of vy, since we just solved for it in our vector calculations, we can input this into this equation. Also, we can put in the acceleration due to gravity, or little g, in for the acceleration in this equation because they're equal. So, Fred is left with the equation of delta y equals v sine theta times t plus 1/2 gt squared. So, after plugging in all of his numbers and solving for t, he ended up getting t equals negative 0.65 seconds, or 1.56767 seconds. And he got two answers because he used the quadratic formula in this case. But since t can't equal anything lower than 0, then that means t equals 1.56 seconds, which means that he was airborne for approximately 1.56 seconds. Now to figure out if Fred's going to make the jump, we can plug t into the other equation that we have available to us, which is x equals x naught plus vxt plus 1/2 at squared. However, we can condense this equation as well into something very similar as before using the same strategies. After doing that, we're left with delta x equals vxt, and you may notice that the acceleration is gone from this equation. And the reason behind that is because there's no acceleration in the x direction, only in the y direction, so we just get rid of the acceleration in anything that it's multiplied by in this equation. But since we can also plug in v cosine theta for vx, we can do that as well. Now we have all the values we need to solve for delta x, or the displacement in the x direction. So after solving for it, Fred found that his displacement in the x direction was 12.15 meters. So, since Fred originally knew that the length of the ditch that he had to jump over was 12 meters long, and that 12.15 meters is greater than 12 meters, he figured that he could make the jump, but only by 15 centimeters. So, Fred will survive, but not by that much. When finishing all of the calculations, specifically solving for delta x, or displacement in the x direction, as he did earlier, Fred determined that he could, in fact, attempt the jump and make it to the other side by only 15 centimeters. So Fred attempted it, and his calculations ended up being true. He made it to the other side by the exact amount he figured. His friends were so relieved that he made the jump and cheered for him. Then they all skied over to a chairlift and enjoyed the rest of their trip at the ski resort before heading home and returning to school.